So what are we going to look at today? Let me just jump on the slide here and make sure this is working. Excellent. So today's presentation, we're going to look at what is a vacuum drainage system. I guess that's really good to get the fundamentals sorted from the outset. And then we're going to look at what components we need to put together a vacuum drainage system. And then why is it beneficial? So why are we delivering these sorts of systems as a consultant or as your customer? Why is this technology going to be important for them? And then we're going to look at some of the design principles, some of the things we look at as a vacuum sewage system designer, and then how to comply as a consultant with AS30 or AS/NZS 3500, which is a plumbing and drainage standard, and section 2 talking specifically about sanitary. And the section specifically about vacuum drainage systems that we put in there. And then lastly, we'll look at some case studies. It's always good to look at how we've applied all of these elements and why the projects that we delivered for went ahead and what were some of those sort of defining factors. So what is a vacuum drainage system? So if you can imagine, I think the simplest way to explain it, and I guess we all being in the plumbing space or in the design mechanical engineering space, I think we understand pressure related systems, high pressure water, gas. If you can imagine a length of pipe, in the middle of the pipe we have a valve. Now, if we build up lots and lots of pressure on one side of that valve, and then we open it, all of that pressure is going to be released through the valve from the high pressure side to the low pressure side. In simple terms, if we look at a vacuum drainage system, it's exactly the same thing. We have that same length of pipe and we have that valve, but instead of building lots of pressure on this side, we build a subatmospheric condition, so below atmospheric pressure. And so when we open that valve, we still have the high pressure transfer to the low pressure, but we're talking about atmospheric to subatmospheric. So anything that might be at the head of that valve, any liquid, wastewater, what have you, when that atmospheric air rushes through, it pushes the wastewater into the subatmospheric condition, and that's our vacuum pipe network. So if we look at that picture on the bottom right, on that, I guess that diagram there, we have that middle bar, that middle point, that's atmospheric sea level pressure. That's where we exist right now. If we look at that absolute 0 point, that's space. That's up in space. So essentially we could run a pipe from a toilet on Earth into space, and you'd get the pressure differential required to transport the waste from Earth to space. We don't want to do that. We don't want to make a mess of space. And anything above that atmospheric pressure is your high pressure systems, high pressure gas, high pressure water, what you might do with pressure sets with water for pumping water into buildings and things like that. You'll see a little symbol there called EVAC. That is the company that we represent, HIFraser Group. We have for probably over 20 years now. And that EVAC group is in all sorts of vacuum systems and spaces. But you see it sits between atmospheric pressure and absolute zero. So we use that subatmospheric condition relative to atmospheric air pressure around us that we exist in to transport waste. And we create that subatmospheric condition in a sealed pipe network. And we always maintain that subatmospheric condition within that sealed pipe network. So we've always got a differential to transport waste as and when required. You may know vacuum technology if you've been on cruise ships, if you've been in aeroplanes. It's existed for many, many years, and that was really the outset of vacuum technology, was in the shipping space. How do you deal with a ship that lists and rolls and moves back and forth? And how do you get gravity drainage when your platform is actually moving around? Now, we don't get that in buildings, thankfully, but that's where that technology has come from. And then you've got planes and trains globally. So we look after maybe 1,200 odd rail toilets around Australia as well. We've got an emerging bus market as well with vacuum toilets. So it is quite a tried and tested technology. It's not new. It's existed for a long time. And for us, with access to EVAC, which is a global business founded or based in Scandinavia, in Finland, we have access to over 45 years of global experience in vacuum drainage systems. And then in terms of vacuum drainage systems specifically in buildings, there's over 3,000 global examples. So we like to think that we haven't come across a situation, or we wouldn't come across a situation when we're talking about projects where we don't have some kind of reach back, some kind of experience from EVAC to be able to support that project. And as Les said, I was integral in part of the group that developed the addition to AS 3500. And that is section 16, which talks about vacuum drainage systems. So it's now a deemed to satisfy solution under the National Construction Code here in Australia, at least. And then we have the watermark technical standards, so Standards Australia Technical Standard 100, which is the watermark technical standard. So we're at 6 stars as in terms of the WELS scheme in Australia. We're a 6-star toilet using just 0.9 litres per full flush. If you has anyone actually, I mean, you can jump off mute if you want to answer this question. Has anyone actually seen or installed, or has anybody had any experience with vacuum drainage systems?
Hi, Chris. It's Ray from Agile Consultancy. I've had experience with vacuum plant with a project in Hamilton for the Te Rapa train depot. So
Oh, yes.
with my previous employer, we were engaged to do design for the Auckland to Hamilton trains. So
Yes.
use a vacuum plant to extract the or decant the effluent tanks from the trains. So yeah, it's quite a unique experience, to be honest. So just
that's
looking forward to
great.
seeing what you guys have to offer.
Yeah, that's right. Well, those trains have our vacuum toilets on it, so it's quite an interesting sort of connection there. Very good. Thanks. Thanks for that feedback.
Cool.
It's not often to find that not many people have had experience with it. You know, it's gravity drainage has worked since the Incas, and vacuum drainage is it's a complementary system. It's an enabler for certain applications, but it's never always going to be the primary solution, and we recognize that. Did anyone else have any experience? No? All good. Oh, we'll move on. So what generally makes up a vacuum system? So we've got 3 key elements to a vacuum system. The first one is how do we make vacuum? How do we create a subatmospheric condition within the pipe network? So we have 2 different types of vacuum plants, and we'll go into detail as to why we'd pick one over the other a bit further down the presentation. But on the right-hand side there, you'll see we've got tank-style systems, and on the bottom right are inline-style systems. Essentially, what we're doing is from day one, when we have a project, before we've turned it on, the pipe inside and externally, we're all at atmospheric sea level pressure. Then when we start up that vacuum plant, we start some pumps that start to pull the air out of that pipe network. And so we start to create a subatmospheric condition. Now that air is being transferred out to a vent, to external vents, disappearing somewhere. And then once we get down to a certain vacuum point that plant is designed to maintain a certain level, the pumps shut off. They don't run all the time. They shut off. And then we have a subatmospheric condition. Then whenever we have connected interfacing units like toilets or what we call vacuum interface units that hold a sort of a temporary storage of liquid from a sink or a shower or something like that before discharging into the vacuum pipe network, when they are flushed, we use atmospheric air to move that wastewater through the pipe network. But in doing that, we reduce the vacuum. Every time we fire a toilet or an interface unit, the vacuum is constantly reducing. And so that vacuum plant there will sit there, and it'll recognize, it'll detect that the vacuum's dropped because we've transferred some waste. And then the vacuum pumps will start up again, and they'll bring the vacuum back down. So we'll constantly maintain a subatmospheric condition through a couple of cut-in and cut-out points in the vacuum plant. For the most part, the top one will temporarily hold the wastewater and discharge it when it gets to a certain level. The bottom one there will instantaneously discharge the wastewater when it's operating. So it works in a liquid ring sort of style. But really, that's it. This is the heart of the system. This is the point that is making the vacuum. Without vacuum, we really don't get any movement of waste. The whole system is, I guess, defunct. And so sometimes, depending on the primary sort of use of the system or what's required, sometimes these will be on backup power supplies, might be on a UPS. But some would say that this is probably, the key risk in a vacuum system is if there's a power failure. But for the most part, if there's a power failure and all the lights go out within a building, more often than not, you're going to evacuate the building anyway. Thankfully, with the tank style system, we do have some residual vacuum. So even if the pumps don't kick in, we might get 3, 4, or 5 flushes. before the system completely is void of any vacuum to transfer any more waste. So the good thing about our technology that we deliver from EVAC is it has a vacuum, it has flush memory. So if you flush the toilet and there is no vacuum available, it remembers that that flush has happened. So next time that the power is generated back up or the vacuum plant comes back up to full vacuum, those toilets, anything that's been flushed when it's been down, will all fire. So that's a sort of fail safe and backup with some of the equipment connected. But really, that's all it is. It's just maintaining a subatmospheric condition within the vacuum system. The next thing that we have in a vacuum system are the toilets and the buffers, the interfaces. How do we take and this really is the other end of the system. The vacuum plant is one end. This is the other end. So how do we bring waste into a vacuum pipe network? So imagine that length of pipe that we had, and we had that valve in the middle. Well, you'll see with these two bits of equipment here, they have a valve on them, and that is an isolation between the atmospheric air and the subatmospheric condition in the pipework. So when a toilet gets flushed, it just uses a pneumatic flush button, and that valve will open. And when that valve opens, you'll see in the picture in the middle of the 5 circles there, it looks like a mushroom valve, and there's a similar one on the tank that's on the top right-hand corner there as well. When you flush a button, or in the case of the vacuum interface unit, there's a small sounding tube within the tank that when the liquid level fills up, we get a certain pressure that will fire that tank as well. That valve opens and allows the atmospheric air to rush in to that pipe network, like that length of pipe with a valve that opens and everything rushes in. A cycle time for a toilet might be 3 seconds. Cycle time for an interface unit that's collecting might be 5, 6 seconds, depending on how much is in there. So it's not open for long, and that waste is moving out of that toilet at a fairly great rate of knots, about 10 to 15 meters per second, at that initial energy point. And really, that's the process of the toilets. Toilets are directly connected to the vacuum pipe, whereas these interface tanks might collect a series of sinks or other hydraulic devices together and temporarily hold that liquid before it goes into the vacuum system as well. But really, that's it. You've got toilets and buffers, and they are the two input points, I guess, into the vacuum system. The tank is the collection point and the end point. The last thing in the system is the vacuum pipe itself. Now, this is really well detailed in the standard. In terms of vacuum piping, we don't mind if it's metallics or plastics. It could be pressure PVC, it could be copper, it could be stainless, depending on what the project calls for. It could be HDPE, up to 50 mil. The standard does go through and specifically talk about, has a list of approved products that you can use in a vacuum system. But really the key thing in there is a minimum pressure rating of PN10. And that's not about a burst, that's about collapse. Now, globally using PN10, we've never had an issue with collapsing pipes. And we've put that in there in the standard. What can happen is, because that pipe network is constantly in that subatmospheric condition, there's actually external pressure on the pipe rather than internal pressure pushing out. There's an external pressure pushing in. So if you get radiant heat, say that pipe sitting outside in the sun, or you get some hot water in there and constant hot water, and you have maybe some inconsistencies in the extrusion of that pipe, you can have a point where the pipe collapses. Now, that's typically drain waste and vent, when people accidentally use drain waste and vent for vacuum systems. But for the most part, for PN10, globally, we've never had an issue with collapsing pipes, and that's why it's in the standard. And smooth and free of burrs and obstructions. You know, that waste is moving pretty quick. It's in a small bore pipe, so you don't want to have anything hanging down in the wastewater flow. Now, as you might remember, I mentioned that the wastewater is moving about at 10 to 15 meters a second, so we need to brace that pipe a little bit more rigorously than perhaps we would with conventional drain waste and vent, where we might sort of put it on single hangers. We like to laterally brace that pipe work, and particularly when we get to places like turns and changes of direction. If you're moving, say, 2 to 4 kilos of waste as a slug through that pipe network, we want to make sure that when it turns a corner, it's not going to bust out that pipe. It's not going to crack anything. We're not going to get rattling around and pipes moving in the ceiling. And so we normally, the standard will dictate that you must secure the pipe within 300 mils each change of direction and at 1500 mil intervals, and that's laterally rather than just on hangers. The really cool thing I love about the vacuum drainage systems are reform pockets. Because we're not reliant on gravity to transfer this waste through the pipe network, because we're using atmospheric air rushing into a vacuum system to push that waste through, the reform pockets help us do three things for us. One, they re-accelerate the wastewater for us. Secondly, they help us get around obstructions. And thirdly, they help us reform grade. So the standard does dictate a few conditions around reform pockets, but more or less, a reform pocket is about a 300 mil rise. And you can see it is in the drawing on the right. We'll go into some more detail specifically a bit later in the presentation. But a reform pocket from a 3-meter lift from a toilet to a ceiling space, using reform pockets in accordance with the standard, we can do a 300-meter horizontal run without any loss in grade. So with a 1% fall on pipework at 300 mil every 30 meters, we can do 300 meters of horizontal run. So this gives you really lots of flexibility in terms of placement of hydraulic services within your floor plate, but it also gives you 100% hydraulic coverage across a floor plate for your customer. So you can bring water in and bring waste out in the exact same route across quite a large sort of area. Sectional isolation valves, we like to put these in. Truth be told, we're going to get leaks here or there. There might be a weld that's not done properly. There might be a connection to a toilet that's not done properly, or we might get a valve that sticks open or something like that. Isolation valves are going to help us to not only isolate a fault so we can repair it, but it's also going to help us to fault find where actually issues are. We'll always have them at the vacuum plant. And so if you've got 3 or 4 lines coming to a vacuum plant, we'll have one for each. So you can isolate it down to 1/4 of the system, and then potentially you can isolate it down from there. Going to the extent of motor operated or monitored valves, the cost burden is probably far too much for a vacuum system. And we've never actually really been asked to do anything like that. So normally manual isolation valves are really all you need. And we'd always isolate a toilet or an interface, like a grey water interface or a buffer or something like that. So as we can service that particular piece of equipment, a toilet's broken or it's at planned maintenance, we close the isolation valve and we can work on that toilet. And no T's and short radius 90-degree connections. The way we keep such small bore piping clean is through self-cleansing velocity. So that waste is moving very quickly. If we have 90-degree changes of direction, for example, a hard 90-degree change of direction, if you can imagine driving a race car down the road and you get to a really tight turn, you've got to slow right down and then you've got to accelerate back out of that corner. But if it's a nice sort of banking turn, well, we can keep that speed up around the corner, and that's what we want to do, particularly when we look at something like a typical branch or a main serving up to 25 toilets is DN50. It's quite small, DN50 pipe. So if we're not moving that waste quickly through the pipe work, we might start to get hang-ups in there. We might get some struvite or uric acid build up in there over time, and we might get to a 40 or a 30 mil bore, and then we're going to start to run into some issues. So we want to make sure that we're keeping that system working as efficiently as possible. We've got the waste moving as fast as possible, so as we can really leverage that small bore piping, which is another one of the great benefits of vacuum drainage. So we're saying there, and these number of toilets are per the standard, but DN50 pipe up to 25 toilets, a DN70 pipe up to 125 toilets in an office application, which is quite considerable. Us as a supplier, there's 2 other suppliers of vacuum drainage systems in Australia. Us as a supplier, we typically wouldn't go above a 75 mil pipe. If we had a requirement to collect more than 125 toilets, we would typically put in a second 75 mil pipe. Most of our risers might be maximum 100 mil, but that's in the vertical, and they're really gravity's gravity. If it's vacuum or it's not a vacuum, waste is going to fall at the same speed no matter. And so we don't mind 100 mil in the vertical, but horizontals typically will stick with 75 mil. So back to a couple of questions here, and feel free to unmute and jump in if you want to answer. Otherwise, I'll jump in and go. It's just sort of a little bit of a recap in terms of where we've gotten to now before we sort of move into some of the more details, so standard information. But can anybody have a go at explaining what a vacuum is?
Gaseous space, less than atmospheric pressure.
Yeah, absolutely. Yeah, subatmospheric space. That's perfect, Les. Thanks. Can anyone think of the two main types of vacuum plant that we use to generate vacuum?
Yeah, I'll go.
I might. Yeah, go on.
It's a holding tank and it's also an instantaneous?
Yeah, inline instantaneous system. Yeah, excellent, Callum. Yeah, that's a tank style system for high simultaneous demand applications and inline systems where you've got less sort of instantaneous or demand like that. Yeah, perfect. Does anyone want to jump in and say what are those two interfaces that we talked about? Really, the two key inputs into a vacuum system. I'll give you a hint. They're on the right-hand side there. The first one is a vacuum toilet there. So we've got the vacuum toilet, which is a direct connection into the vacuum system, and the other one there is a vacuum interface unit that we use for collecting grey waters, sinks, drains, showers, and what have you. Really quick one, what is the minimum pressure rating for any vacuum pipework?
Where is it?
PN10?
PN10, perfect. Well done, straight ahead of the class. And just the last one there, what document would you refer to if you wanted to find out what the design requirements were for a vacuum drainage system?
3502.
That's it, section 16. Well done, Liz.
I've just got another one for you, Chris, actually. That,
yeah, absolutely, yeah.
With the small bore and your speeds of 10 to 15 meters a second, small bore, but you're going to increase your frictional loss. So how does that work in? I know HDPE or P plastic's got very low frictional loss, but you're still going to pick up a hell of a lot of friction. How does that affect the system?
Really, that speed is at the instantaneous point when we open that valve, and that's at your maximum differential between your atmospheric external and your subatmospheric internal. So once that waste has moved up the riser and into the horizontal piping, generally that liquid's going to drop to the bottom of the pipe, and that air condition is going to equalize over the top of the liquid. And so we always have that 1% gradient direction of the vacuum plant to make sure that as that liquid slows down and settles in the bottom of the pipe, that it's running towards a reform pocket or the main riser. But yes, it's generally for that initial 3-meter lift from the toilet to move the waste vertically. We reduce the pipe size and we increase the velocity for, say, Costco, for example. We'd have a 25 mil riser pipe, and that we can lift 7 to 8 meters. Really, 10 meters is kind of the maximum in terms of liquid slug. It's 10 meters is 1 bar is the complete differential between sea level and absolute zero space. But yes, it's a good question. But by the time it's gotten up the riser and into the main, generally it's only going to move at that 10 to 15 meters initially, particularly over a reform pocket when you get another dose of atmospheric air coming in from a toilet flush, and at the back of a reform pocket where it kicks up and moves again, you'll get that instantaneous move of the waste vertically over the reform pocket, but then it's going to slow down pretty quick and it's going to run down the bottom of the pipe. But I would say, as a general thumb, 90% of the pipe is fully open. There's only generally little liquid pockets at reform pockets around the system, but for the most part, all the waste is going to be back at the vacuum plant a pretty quick amount of time. Does that answer the question there, Les?
Yeah, that's fine.
Yeah. Awesome. All right. So as engineers and as consultants, why is this beneficial? And I've sort of taken the liberty of listing a couple of projects where we've had either EVAC's had global experience with, or we've had direct experience with, where we've looked at projects. But definitely facilities requiring dedicated or protected waste flow. So these could be hospitals in some other countries where they've got to hold their the radioactive medical waste for the half-life of the material before discharging it to the sanitary system. Using just 0.9 litres per flush, well, then you've got a significant reduction in the amount of liquid you've actually got to hold, how big that room is. And then that vacuum pipe network from the toilet to those tanks is under a subatmospheric condition. So if you do get a leak or something like that, air's going to be rushing into that pipe rather than liquid dripping out of that pipe. So it's a very sanitary way of moving particularly hazardous waste, bio waste. I know Sydney has the Murray-Bashir Biobank where they do studies of blood and those sorts of things. Again, very hazardous waste. And so being under a condition where that wastewater can't drip out of the pipe if there's a leak makes it very safe. But it also, in terms of vermin moving up through the pipework, it can't be done because we have a physical interface between the toilet or the interface to the pipe network, and then there's a tank on the other end as well. So they've kind of got to get into the tank and into the pipe. So it's very safe from vermin. And then also in terms of being on a subatmospheric condition, it's very hard for bacterial growth in a subatmospheric condition as well. So it's a very, very clean way of moving particularly hazardous wastes, if that's sort of if that's where the project is calling for that. And particularly in prisons, there is an interesting one. So there's several prisons in Australia that are on vacuum drainage. And the benefit of that is that they can isolate the vacuum to restrict toilet flushing during contraband inspections. And they also reduce the risk of contraband transfer between toilets and between cells through the sewer system as well. I mean, you give a guy in a cell 23 hours of when you've got blank walls and a stainless dunny, they're going to find ways of doing all sorts of things. So it enables some of that security for the prisons as well. Particularly projects where under slab access is limited. So we've looked at projects where you've got shopping centres built over train lines, for example. We had a project for a a police station in Sydney, in Manly. They are built over a stormwater outflow. So they had to change all the custodial cells in the basement, but they couldn't actually they couldn't actually dig into the floor because they had the stormwater piping underneath. So we were able to use our vacuum system. It's a hybrid system. The rest of the building is all gravity, but just the basement is under vacuum. Just mute that one there. Someone come in. So there we go. Perfect. Thank you. Supermarket. So as you may know, we've done the Costco in Auckland there. So if anybody's been to the Costco, if you go down towards the meat section, there's 2 high cases and 3 low cases. There's a pie case and there's also a flour case. And if you look up, you'll see our valves up in the ceiling. So we do all Costco's in Australia and we do them in New Zealand. And in fact, they've had such good experience with the project at Auckland that the same guys that installed that system are now looking at us for a different supermarket that's having issues with block drainage pipes in the ground and they haven't been able to resolve it. So they're looking at a vacuum system for that. Definitely eliminate the cost of trenching, core holing, particularly in a shopping center as well. A lot of shopping centers don't like their slabs being turned into a piece of Swiss cheese. And so what a lot of supermarkets will do is they'll put provisions in to be able to move the fridges around. But with a vacuum system, we have our little interface that sits on the floor underneath the fridge, and then the pipe goes to the ceiling. So if you want to change the design of your supermarket, what will often happen is you'll have to shut down a quarter of your store for a week. You'll have to re-core hole, drill, and do all that, and you've lost your customer base for a week. They've found out they can get their milk and yogurt cheaper somewhere else, and then you're trying to rebuild your customer base after a week. Whereas with a vacuum system, they've moved the fridge overnight, they're back up and running the next day, and there's no impact on their operations. And when we've done supermarkets in the past, they've done staged openings. So we put the vacuum plan in, and they've done a quarter of the store, opened it, done a quarter of the store, opened it, and so they've been able to open the store in sections, and we've isolated the vacuum system as we've opened up each section. Sites with large instantaneous flow rates. So Optus Stadium over in Western Australia is built in a very marshy sort of soil. The ground is terrible to try and do any work in. And so a lot of the lower level stuff is on a vacuum system, and it actually lifts it back up to the promenade area where you've got tanks. So there's actually a sort of I guess a 45-degree angle lift back up from the actual ground, the sporting field, back up to a promenade area. where typically in the ground, the water would have just basically filled up all any trenching. So very high water table sites as well. Sites below sewer level to reduce and eliminate wet wells. So imagine you've got 10 or 20 wet wells around a site because you've got 10 or 20 risers going up through the building. If you can replace those 10 wet wells with a single vacuum plant, let's say you've got 2 pumps per wet well, well, you've reduced the maintenance of 20 pumps and the risk of 20 pumps. You've got all the cost of installing those wet wells are all reduced down to a single vacuum plant with 4 pumps. And so in terms of your OPEX down the track, there's reduced cost. And because the pipework can run horizontally without any loss in grade, we can bring all those risers down back to a single vacuum plant that then can pump out to a single sewer provision. Short schedule commercial fit outs, we do a fair few of these. We've done childcares, we've done sort of office installations, end of trip facilities, those sorts of things where I have this corner of the car park and I want to put an end of trip facility in because we can charge a slightly higher rent for our office space because we provided EOT facilities. And so we can go in there and without drilling or chipping into the flooring, we can install all hydraulic facilities in there and extract the waste back to the existing sewer stack within the building. Simply and quickly, you can get in and get out and get the job done. Green Star is obviously there's a benefit having 0.9 litres per flush for green projects. The way that green projects are worked out, it can be quite hard to get a vacuum system across the line just on water savings. Water doesn't cost enough. That's the problem. You can save a ton of water, but it might at the end of the day save you $1,000 in a year. And so the return on investment just doesn't stack up in that. And that's why we find that vacuum systems are actually far more applicable to overcoming technical challenges in the project versus just a Green Star. Where this did stack up, and we'll do I'll do a review of that case study towards the end, is the Living PAR in Wellington Uni, and that is a living building challenge project. It's purely based on rainwater, and so having low flush toilets, very low flush toilets and rainwater made sense on that particular project. Mobile and transportable facilities, so like festival toilets and those sorts of things. So instead of having individual toilet blocks around the actual site that need to be individually emptied, you can daisy chain all those together into a single pipe and take it out to a single vacuum plant, which then can discharge out to a bladder that's off-site. And so you don't need to bring your tanker truck into the festival and have the smell and everything going on and while you're trying to empty those individual tanks. And lastly, heritage buildings. We're not restricted by gravity. We can take pipes over, under, around, up. And so we can avoid heritage infrastructure in heritage applications. So if you want to, and we have found that the net benefits come from, if you use conventional drainage, you might be able to get 20 rooms into your hotel in this heritage site. But using vacuum, you can then add 30 rooms because you're not limited by the provisions for penetrations through for your drainage. And so, well, then that's 10 extra rooms at $700 a night, times by 365. Well, then there's your return on investment comes within 6 to 9 months of the project, for example. So generally, and the last one there, Green Star and LEED, if the path you want to go down in terms of that, generally Green Star, you're getting about 6 points, and for LEED projects, you're getting about 8 points on the project just because we're at 0.9 litres per full flush. All right, so we'll go through these quickly. Generally, these are the things that we look at. There are 2 other vacuum system suppliers in Australia, and globally, everyone's doing it their own sort of way, shape, and form. What we look at, and if we were working with you on a project, what we're going to look at first is the building type and the application and the location. These things are going to determine frequency. So, is it an office tower? Is it a hospital? Is it a stadium? Is it an airport? Or is it end of trip facilities? What is it? And that's going to help us look at things like the usage frequency And we provide, well, we apply reduction factors. We will do a general calculation based on the number of fixtures, and then we can ramp that up depending on if it's a high use application or if it's a standard low use application. And that's going to help us determine, do we need a tank style plant or do we need an inline style plant? How high do we need to discharge that waste out of that site? How often do we need to discharge it? And things like external pressure levels. So it might sound sort of like a silly one. Aren't all buildings at relatively close to atmospheric sea level pressure? Well, no. The guys in France installed a skiers refuge in Mont Blanc, and that's at some crazy elevation up in the French Alps. They actually had a problem with using centrifugal pumps because all of a sudden we had sea level atmospheric pressure here and we have absolute zero here. All of a sudden, when you're at elevation, you're now only working about 70 or 60% of that range because your relative atmospheric air pressure is actually much lower. And so they had to run positive displacement pumps to generate sufficient vacuum to operate the toilets. So these are all little things sort of we look at on the project to make sure that what we're going to specify is going to be the right product to suit the project. Obviously, we want to know how many toilets, how many showers, how many sinks, how many kitchen sinks, washing machines, pan washers, whatever else, pit drains, those sorts of things. What are the elements on the project and where are they located, and how do we want to collect those? Particularly, is this a stage 1 of 5 or is this the full development? Do we need to make a plant that's 5 times as big because we know we've got 5 stages coming, or is this the whole project in itself? And the last one there is the key drivers. What is it? Why are we going down this path of vacuum drainage? And as I said earlier, gravity drainage has worked since the Incas. We recognize that. We recognize that vacuum drainage is not for every project. There is a capex difference for a greenfield development. If we're not trying to overcome any challenges, it's going to be more costly for a vacuum system. But as you go through and you start to introduce some of those technical challenges on a project, you need to start adding technology in the gravity space to make this project work. You're going to get to a point where we're going to become on par with the vacuum system, and probably quickly thereafter, if it's a troublesome enough project, it's actually going to be more costly to do gravity, and then the vacuum system is going to start to make sense on this project. But we need to know that. We need to get a really good project brief together, because we might want it, so you might want it, I might want it, but if the end user, the building owner, the developer's not on board, we'll be valued engineer out. And that's most often the case. So we'll go through that effort and that experience, but not sort of see any fruits of our labor. The next thing we need to do is once we've worked out that this is a project that vacuum drainage is really going to be suitable for, we'll look at the size of type and size of vacuum plant we want to use. And we did cover this already. So tank style systems and inline style systems. We've used a mix of both. Some suppliers in Australia purely use tank style systems, and that extraction system for the train would have been a tank style system because you've got a lot of flow through a 3-inch pipe that's coming out of that tank, and there's going to be a lot of demand on that tank. So that would have been a big volume tank, lots of liquid. And then we have the inline style systems, which are typically used for low simultaneous vacuum, 1 flush, 1 flush, 2 flush, 1 flush. And I'll explain the reason for that. In a vacuum system, every toilet, when it flushes, uses about 60 litres of air per flush. And if we have 200 litres of air in a pipework that we've been able to pull the vacuum on, a single flush is going to use 60 litres of that 200 litres of air. And so we're going to collapse the vacuum pretty significantly and rely on the pumps to come back up. If we have 2 flushes, well, then there are 120 litres. So we're over 50% of the available vacuum is being used immediately, and we're relying on the pumps. So in that case, we would then consider using a tank style system where in a minimum tank, we might have 500 to 1,000 litres of air or available vacuum that we can use. And so that 2 flush, 120 litres of demand on 1,000 litres, we're not going to see much of an impact. In fact, we could 3, 4, 5 flushes. Think stadiums, airports where you've got really high simultaneous demand, half time, full time. Whereas an office application, 1 flush, 1 flush, 1 flush, you might get a little bit of peak during lunch and morning and afternoon, but it's definitely not going to be on a stadium level. So we're going to balance that out. Sometimes you may not even be able to fit a tank style system in. It's just going to be an inline style system because we've put vacuum plants in elevators before and taken them up to individual floors in office towers to do a single vacuum system for one floor within a building. Next, we're going to want to look at the vacuum capacity. How much vacuum really do we need? And you'd be sort of familiar with the K factor or the reduction factors for potable water flows, and we do the same thing with vacuum systems as well. And what are those overall wastewater flow characteristics? How do we design a system that is going to be? It could be that you have a system that's purely just vacuum toilets, and so we're going to need lots and lots of air because they're using 60 parts of air per flush to 1 part water. And so you don't need a big tank because there's not much water. There's 0.9 litres per flush, but you need lots of vacuum capacity. On the other hand, if you've got lots of hydraulic devices, lots of showers and sinks, but not many toilets, well, that's down at 4 to 1. So you've got 4 parts of air to 1 part water for that hydraulic. So you don't really need as much vacuum, but you need lots of volume of storage for all that liquid to come into. Otherwise, you're going to basically flood the system. So we're going to balance that out. Normally, it turns out to be 50-50 or more often than not a full vacuum toilet system because that's where the maximum benefit is. And we'll add on a few hydraulic devices because it's convenient. Generally, that's what we're looking to in terms of vacuum capacity and recovery capability. How much vacuum do we need to make sure that, and the standard does define that there is a minimum recovery period. So a minimum recovery period after the activation for something to be reactivated, and it's about 10 seconds or thereabouts. So if you fire an interface unit or a toilet, it must be able to fire again within 10 seconds. And so we're taking that into calculation when we're designing how big the pumps need to be. Discharge capacity and frequency. Again, with that full shower system, we need a tank big enough, and we like to sort of restrict our discharges to once every 10 minutes or 6 times an hour. It's a general rule of thumb. It works pretty well. We don't want the system constantly discharging liquid while we're generating vacuum, just constantly cycling through like this. So if we have a slightly bigger tank, well, then we have time for the liquid to come in, temporarily hold, and then discharge. And so we're going to size a tank that's going to be able to meet that sort of requirement. And then pipe runs and expected losses. When we're using vacuum, these are the losses we're talking about. There's a slight loss, and these might, and I might be a little bit behind the 8 ball in terms of this, but this might be in terms of the friction that you're talking about as well. There is some element to the losses in terms of the wastewater movement and the friction that's from the pipe wall. But we sort of look at this and we talk about a total cumulative lift or loss of 6 meters. So that's how we can calculate that sort of 3 meter lift from a toilet, and then 10 reform pockets at 300 mil lift each. And that gets us our overall 6 meters of loss on a pipe network. The standard does dictate cumulative loss or cumulative lift. So the toilet plus every single reform pocket of 6 meters. And that is really, it's a safety factor to make sure the system's working at its most efficient level. And so we're going to look at the system, how far the pipes need to run, where do we need to locate the plant to make sure that we're within those limits. So how do we comply with the standard AS 3500.2? It was developed by a vacuum drainage special interest group under the Plumbing Products Industry Group within Australia. And that was due to industry regulators forcing us to create. Now, it's not the interpretation of the standard, but we weren't able to get any approval for any more performance-based solutions because their interpretation was that once you've done one, you need a DCS. It's not the case, but you know what? We took 8 years because it was changing from Standards Australia to the ABCB at that time. The standard was moving to the NCC as well. We took 8 years, but we got there. We now have a DCS solution with AS 3500 vacuum drainage systems. And the goal of that was to provide a general overview. Now, it's always good to come back to a vacuum system supplier to really get into the weeds of any kind of project. What we really want to do as well, and like most standards do, is just protect the industry from substandard practice and substandard product, but also people that are unaware that you can't hook a 100 mil outlet of a toilet into a vacuum system easily. And in fact, the toilets that we use on vacuum systems under the Watermark technical standard have either a 40 or 50 mil outlet within the standard. So if you want to have a compliant toilet, it must only have a 40 or 50 mil outlet on the toilet. So that's really what we wanted to do. And please don't confuse this section 16 of AS 3500 with what's under the WASA code. There is an element within AS 3500 which talks about municipal vacuum seal systems, where you have sort of 3-inch piston valves. There's a few of them around, a lot of them over here in Australia. That's a different one. They're municipal sort of utility operated vacuum systems versus these vacuum systems, which are defined as being confined to a single structure, a single building, or a series of buildings on a single basement, if you like. So you can't connect this building over here and this building over here and this building over here into the one site. They would need to have individual vacuum systems if they weren't connected by a common basement. So some key points, no matter who you go to for a vacuum system, they're all going to be providing you a system that's going to be an assembly of pipes fitting as an apparatus that to collect and convey and discharge from fixtures to the sanitary plumbing and drainage system. So really that is the definition of what a vacuum system is. In general, it's going to consist of these elements, and these are really sort of verbatim out of the standard itself. You've got your vacuum station, which we've talked about. We've talked about our vacuum pipe network, and we've got our vacuum soil fixtures, which are toilets, and then our vacuum automatic interface units, which are buffers that we referred to, which are the collection of grey waters into that intermediate holding tank before it's discharged into the vacuum system. So some of the design requirements, we really only have 10 meters of atmosphere, 1 bar of atmosphere between atmospheric sea level pressure and absolute zero. So we operate on gauge versus absolute, on gauge pressure of -35 to -70. And because we've really only got 1 bar or 101.3 kPa, we really like to, a very simple way of referring to it is -35 to -70% vacuum. That's sort of the range that the vacuum plant should operate in. And that gives you a nice safety margin for everything to be able to fire and to move the waste efficiently. When I mentioned before in terms of lifts or losses, here's the cumulative vacuum lift. Shall not exceed 6 meters. And the standard does define that as like a lift and then a little lift and a big lift and a little lift. And it says A plus B plus C plus D must not equal any more than 6 meters. The pipework shall not have or not include 90-degree junctions. So these are really the way to get around this is twin 45s or using Y branches or those sorts of things. And that was to do with the speed of the wastewater moving through the system. We want to make sure that we keep it moving quickly and efficiently. And at change directions, those change the direction need to be twice the radius of the pipe. So they're normally long radius 90s or twin 45s is how we do that. In terms of inspection openings, no more than 1 change of direction. That can be a branch coming in, that can be a toilet, that can be at our reform pockets. When you see on the next slide, you'll see the reform pockets. There's points there to add inspection or rodding points. And we just basically include those throughout the system for safety. Sometimes, let's say the system has been in operation for 10 years, it's purely on toilets itself. We might start to get a bit of struvite or uric acid build up within the pipework. And so as we are vacuum system specialists, we have means and ways of cleaning out that vacuum pipework as well. So we might use that point to connect in to do a pipe clean. And the last one there, maximum temperature of wastewater conveyed should not exceed 60 degrees. And so if you water boils at 100 degrees at atmospheric sea level pressure. So if you increase the pressure, water boils at the higher point, but we're in a situation where we've decreased the pressure, water boils at a lower point. So 60 degrees is a safety point to make sure that we don't vaporize that liquid as soon as we open the valve and introduce the subatmospheric condition. We can use ways of using exposed piping, for example. We can have longer runs of pipework to our interface unit to try and cool that water. But the rule there is 60 degrees C is a maximum inlet temperature of any water into a vacuum system. The next point there is talking about how do we size vacuum pipes in a vacuum pipe network based on how many fixtures we want to connect to it. So vacuum pipelines there shall be sized in accordance with Appendix F, figure 16.4.5, and I encourage you to go and have a look at that after this. Really, that's a large sort of building diagram, and it talks about connected fixtures here into a 50 mil pipe, and then as we go down the building, the pipe becomes a 75 mil pipe, and then as we go down, it becomes 100 mil. And what that's talking about is more fixtures connected mean a larger pipe bore to transfer that volume of waste. So if we look at those tables F1 through F4 there, and it's quite a sort of a simple application of that. The first one is talking about a single vacuum buffer. This is a hydraulic interface unit for showers or sinks or drains. So into a 5-litre vacuum interface unit, we're talking about a maximum inflow of 0.25 litres per second. And then down the bottom into a 100-litre interface unit or a 100-litre tank of inflow, we're talking a maximum of 4.5 litres per second. And then the next one there is talking about, so once we know how much water we can expect, we can then equate what that is as a vacuum loading unit on the vacuum pipe network. So for a 5-litre buffer, which is really the biggest we go, for us, they're the most efficient. Or third from the bottom there is the vacuum water closet pan, is also 4 vacuum loading units. And you might have a 20-litre buffer, which is 12 vacuum loading units. And then applying that to table F3 then says that on a 50 ml pipe, we can have 100 vacuum loading units. So for example, that might be 4 50-litre buffers, or that might be 25 5-litre buffers. Any combination of those vacuum loading units equating to 100 means that we can put that capacity onto a 50 ml pipe. So you can look at there, we might be 15 toilets, which is 60 vacuum loading units, and 10 5-litre buffers, which is 40 loading units, equates to 100. So we can put 15 toilets and 10 5-litre buffers onto a single 50 ml pipe. And we've done it, and it works. so you know, in principle, it actually works. And I think I mentioned before, we really don't go over a 75 or a 3-inch pipe, which is that DN80 pipe, which is 600 vacuum loading units. If we needed more than that to keep water efficiently moving through the pipe and not having that equalization of the atmospheric air and the vacuum over the top and slow liquid flow underneath, we'd like to keep that nice slug of liquid moving through the pipe. So anything over 75 mil, we'd normally add a second pipe. And then the last table F4 there is talking about, and fun fact, it's a misprint in the standard. It should actually say maximum number of vacuum toilets rather than number of vacuum loading units, which is a duplication of table F3. So we're saying on a 50 mil pipe, we can have 25 toilets. On a 65 mil, 100. On 80 mil, 125 vacuum toilets. And that's generally in an office application, because then you've got to add those sort of reduction or the K factor to it to work out whether or not that toilet's can be flushed every 2 minutes with a 2-minute turnaround time. Well, then we've got a heavy use application, so we might be safer to actually pull back on the number of toilets we have on there. Greater pipes, 1% in direction of flow. So 1 in 100. On the cruise ships, we go up to 1 in 500. But 1 in 100 is a safe bet. It just means that any liquid that happens to remain in the pipe that's not completely transferred through the vacuum plant will always dribble down towards the vacuum plant, and it'll either get to the vacuum plant or it'll get to a reform pocket where we can step it up and then let it fall, step it up and let it fall. So here's the reform.
Chris, we're right on time now. I think we're about to get cut off. We're on 12:59. That was absolutely fantastic. That was a brilliant presentation, very, very interesting. And certainly on behalf of CIBSE New Zealand, thank you to everyone for attending, and thank you for doing a superb presentation, Chris.
No worries. What I might do, Les, if it's all right.
Yeah, go on.
Yeah, I was going to say what I might do is actually share this, because there are a few sort of case studies at the end here. But what I might do is share this presentation as it is now with you, Les. And if you want to send that out, my details are on the screen as we speak there. If there's any particular projects that you're looking at, happy to have a chat about them. If you did have any sort of follow-on questions, happy to receive an email from you. But I think, Les, it'd be good if you could maybe send this presentation out. I can send it to you as a PDF if that helps.
I will do. That'd be fantastic. And my apologies to everyone. I forgot to tell you it was all being recorded. I realized a bit too late. I should have said something. So I do offer my apologies about that. But this has been recorded and this will go on the CIBSE website. Excuse me.
Yeah, I think the only thing we missed there was just the case study. So we got through the good bulk of it there. So that's good.
Brilliant. All right. Well, thank you, everyone, and enjoy the rest of the week.
Lovely.
Cheers.
Thank you, Les. And thanks everyone for attending.
Thank you.